Alright, section 12.5 talks about lines and planes in space. So we're going to start with lines, and then we get to planes later on. For now, if I look at lines, in 2 dimensions, in R2, to find an equation of a line, we need a point and a slope. And we would work out y minus y1 equal m into x minus x1, or this is point slope form, y equal mx plus b, in which this is the y-intercept and this is the slope. Now, to find an equation of a line in R3, line L, given point or a point x sub 0, y sub 0, z sub 0, call that point p sub 0 or p naught, and this is on line L, so the point must be on the line itself, and the direction of the line is defined by a vector v. Any vector that's parallel to the line. So, if I look at a line, here's 3D. If I'm looking at a line L, what I need a point on the line. Let's say that's the point right there. That's P naught. What I do, I get a vector from the origin, and I label that vector r sub 0. So whatever the point is, I give it ijk, make it a vector. Now, what I need direction. This direction that I mentioned, suppose it's right there. Let's say that's vector v. What I do, I will take from the origin a vector to wherever that v terminates, and I'm going to call this r, point r. Now, I set r sub 0 to equal x sub 0, y sub 0, z sub 0. And I set my vector r to be, and if you look at that based on what we did before, wouldn't you say that this vector here is the sum of this plus this? Wouldn't you say that vector r is r sub 0 plus vector v, because that's the resultant, if you remember? So I could say here, look, this vector v is r minus r sub 0. So given the point on the line, I can figure out, I could call that the initial vector, r sub 0, and my vector v is any r minus r sub 0, and the equation of my line would be r equal r sub 0 plus t times v, where t is a scalar. And if you really pay attention, you would notice that this right here resembles my b, and this right here resembles my vector. And just like x is any real number, t is any real number. We call this, and that's very important to get the names, there are 3 of them, 2 we're going to focus on, 1 I'm going to mention. We call this a vector form of a line. I changed that a bit, just put the vector form of a line above. Now the same line, if I write this line as, and remember that this r that I chose could be any x, y, and z. So this r, if I write this component-wise, I'm looking at vector r, which is x, y, z equals x sub 0, y sub 0, z sub 0, plus t times v. I'm going to call v a component vector with a, b, c to separate between x sub 0 as a point and a, b, c as the components of the vector. I'm going to call this a, b, c. So the key is always finding that v first. The point is going to be given all the time. Just like in algebra, you are always given the point, you always have to find the vector. So if you really work this out, if you sum those vectors, you'll notice that this is going to be component-wise x sub 0 plus at, y sub 0 plus bt, and z sub 0 plus ct. So this is my vector equation. I always find this first. From this arises 2 more forms. There is a parametric form of a line, and that's simply saying take the x right there and set it equal to the I component. Take the y and set it equal to the y component. And take z and set it equal to the z component. Now, what's important about this, it's a parametric equation. It could possess direction. For different values of t, you could get a direction out of this. And something we're going to need to know, there is another form we're going to use a lot. It's called symmetric form of a line. That one we're not going to focus on. If you solve this for t, subtract the x and divide by a, subtract the y and divide by b, and subtract the z and divide by c. And since t is the same, that's called a symmetric form of a line. Again, we're not going to focus on that. We're going to focus on those two. Normally, whenever they're asking me to find, I'm really after find equation of a line. I'm after looking for the vector form. Now, if I take my first example, and I have plenty of those, directions, find an equation of a line. I want to find the equation of a line through the point 3, negative 4, 1. There's my point, and it's parallel. Perfect. Any vector that's parallel will do. So, my equation is, and I'm going to write this multiple times until I get it. Remember, I'm going to take r sub 0 and set it to be the point from the origin. And my v is actually the 2, 5, negative 6. That's very simple to do. So, I could say my vector r is 3, negative 4, 1 plus t times 2, 5, negative 6. Or simply r equal 3 plus 2t, negative 4 plus 5t, and 1 minus 6t. So this is the vector form of a line. And no big secret, if I want the parametric, x equal the I component of that vector form, y equal the j component, and z equal the k component. This is parametric form. Later on, we're going to put a value on t if we want to have direction included. Symmetric, solve for t, subtract x from both sides, divide by 2. Solve for t, add 4 to both sides, divide by 5. Subtract 1 from both sides, divide by negative 6. Since that's t equal, and t equal, this is symmetric. Again, I'm not going to keep on finding symmetric. We barely use it in this class. We are going to focus on those two more than anything. And here's another problem. They give me 2 points. Well, I could take r sub 0 to be either of those. I could say let r sub 0 be, it doesn't matter which of those. Let's say 2, 5, 3, go in that order. And to find v, well, I could find v by taking end minus beginning, 5 minus 2, negative 2 minus 5, and 11 minus 3. And now I could say my vector equation is 2, 5, 3 plus t times a, b, c. A is 3, b is negative 7, and c is 8. And I could say r equals 2 plus 3t, 5 minus 7t, and 3 plus 8t. That would be my, again, vector. I'm going to keep on mentioning that until it sticks. In the beginning, it's going to seem to be a bit of work. Later on, this is going to be second nature. And if I want to write this in parametric form, I know how that goes. X equal 2 plus 3t, y equal 5 minus 7t, and z equal the k component. Again, different values of t will pretty much give me different points on the line. Whenever direction is involved, I need to give a value for t that's coming up. You would know that when they say go from this point to this point, now direction is a must. And in that case, you're going to have to really look at the values of t. Or whenever they say parameterize, I can never say that word right, the following. How about this line? I want a line through the point. Okay, the point, that's very good. They gave me the point. They always do. There it is. I just make it a vector from the origin. Now I need the direction. I need this line to be perpendicular to both of those. Well, how am I going to do that? I need it to be perpendicular to 1, 1, 0 and 1, 0, 1. Well, I know if I cross those two, if I am to take 1, 0, 1 and take the cross of those, again, this notation is mine. Cover the I component, 1 minus 0, that's 1. Cover that J component, 1 minus 0 is 1, don't forget the negative. And cover the K component, 0 minus 1. There is my vector V. And now that I have V and I have R, well, guess what? Pretty much I'm done. R equal R sub 0 plus V times T. And my equation is actually R equal 3 plus T, 1 minus T, and negative 2 minus T. There's my vector form. Parametric form, I know how that goes. I'm going to say x equal 3 plus t, y equal 1 minus t, and z equal negative 2 minus t. This is parametric form of the line. Now, something I need to elaborate on and show you right now. This is going to help us for a plane as well. I need to review with you a bit of algebra, something probably you passed on but you never paid attention to because it wasn't brought to your attention. It's not that challenging, but let me go over that with you. So, given ax plus by equals c, I'm talking about 2 dimensions. So an example of that, 3x plus 2y equals 6. If I sketch a graph of that line, when x equals 0, y equals 3, when y equals 0, x equals 2, there's my line. A perpendicular line to that, do you notice to get a perpendicular line, you would have to solve this for y. I could have, of course, said start on 3 and run 3 down, 2 to the right. But do you notice the relationship between those and those? The slope of the line is really negative 3 over 2. To get a vector, to get that in vector, the I can, remember this is the change of y over the change of x, which is really my j component over I component. So to get any vector in that direction, the direction of this, that is simply a multiple of this will do. Now, if I say I want to find a perpendicular vector to this, or a perpendicular line, the slope will be the negative reciprocal, 2/3. If I want to write that as a vector, that is, did I do this right? Y, the change of y over the change of x. There we go. And no big secret, if I draw this vector 1, 2, 3 and go up 1, 2 and draw that vector right there, guess what? Those will be perpendicular. But did you pay attention to what just happened? Do you see that this is a line, and if I wanted a vector perpendicular to the line, I simply take the components 3, 2. The reason that works, when I solve for y, I am getting the negative reciprocal of that. So what does that mean to us? In 3 dimensions, something we're going to have to do a lot. If I'm given a plane, if I'm given 3x plus 2y plus z equal a 6. In 3D, let me plot that really quick. In 3D, if I look at, actually let me make that negative 3. And the way to graph a plane in 3D, it's very easy. Zero out the y and the z. X will equal negative 2. Zero out x and z, 2y equal 6. That means y is 3. And zero out x and y, z will equal a 6. And if I connect those with, this is a piece of the plane, not the whole plane, a piece of it. The plane is infinite, right? The plane is really in that direction. Now watch what happens when I take the vector negative 3, 2, 1. Negative 3, 1, 2, negative 3, 2, and 1 up. If I draw that vector, that vector touches at 90 degrees. It's perpendicular. We call it normal. Normal vector. A normal vector is a vector that's perpendicular to a, specifically we're going to be dealing with a plane. Something that's coming up in the second half of this lecture. And let me just elaborate on that last example. Where are we now? C. We are in D. I don't know where that says 1. Find me an equation of a line in 3 dimensions. Well, hey, no big deal. R sub 0 is 1, 2, 3. It's always given. I need a vector parallel. Well, find me a vector, a line through this point perpendicular to this plane. Well, isn't any multiple of that vector perpendicular to the plane, whether you extend it forward or whether you go backwards? It doesn't matter. That's going to be perpendicular no matter what. Isn't a vector perpendicular to the plane 3, 2, negative 4? And now, if I want to find the equation, well, that's simple. All what I have to do is write R equal R sub 0 plus t times this vector. And that would be R equal 1 plus 3t, 2 plus 2t, and 3 minus 4t. And when we meet in the discussion, I would be more than happy to show you graphs of those on GeoAlgebra. And you could see that clearly. Right now, I really have short on time. X would be the I component, Y would be the J component, and Z would be the K component. Parametric. And this is a vector form. I'm going to stop this video here and start talking about a plane in the next video.